So, this is an experiment on coupled pendulum, right, and it is basically two simple pendulum coupled with some kind of a coupler. So, now what we have is this is my setup, and as you can see we have two simple pendulum here. We have used a scale here so that we can also do length measurements, right, and there are two bobs which are I think approximately 1 kilogram, right. So, this is my simple pendulum. Length of the pendulum is about 63 centimeters. So, with that information one can calculate what is the natural frequency for this too. Okay. Now, of course, what we can do is we can displace the pendulum slightly, let us say one of these. Right now there is no coupling, right, and we can see its oscillation. We can measure the time period, we can measure the amplitude, we can see how the acceleration changes as a function of the position of the bob and all these things, right. However, that more or less gives us a qualitative observation and information regarding the behavior of the pendulum. To get more quantitative information and then to analyze it further, what we have done is we have actually combined the pivot. So, the pivot of the pendulum is a ball bearing which rotates when the pendulum oscillates, and we have combined this to a potentiometer pot, right. So, a normal 1 kilo ohm or 10 kilo ohm variable resistor, right. So, what happens is when the pendulum makes a swing or makes a swinging motion, the pivot rotates and the rotational motion of the pivot is then transferred to the rotation of this variable resistor, right, which is connected to a 5 volt supply using this box. So, now as the pendulum makes sinusoidal oscillations back and forth, the resistor, the resistance value also changes about its mean value, slightly going higher, slightly going lower in each oscillation, and that in turns gives us a variable voltage output about a mean, right. So, that is the way, and you will see later on in several experiments, that is how lot of this mechanical motion is converted into electrical signals. To see this into a digital PC or a digitizer, what we have is something called a analog to digital converter device, this box where the output of this potentiometer voltage is fed into here, and this is a device which is converting analog signal into digital signals with 12-bit precision. Double click on the software, we can start this menu, and what we see is after going to certain settings which are not important at the moment for you, we can get a voltage versus time plot. Disturb this slightly, one of these, so that it starts oscillating, right. And now I can start measurement on the PC, and what you start seeing is an oscillatory waveform. Now, of course, one can observe several oscillations and then try to find out the time period for this motion. So, what we can do is we can stop the measurement here because we have taken something like 30 seconds of data. We stop the measurement here. So, it shows us the data taken over that time. Now, many times, since if our resolution is very large compared to what we actually desire, we get some kind of fluctuations in our acquired data. So, in this particular case, we can run a simple smoothing algorithm which basically takes nearest 3 points or nearest 5 points and then averages out the mean value to smooth out this curve, and then this is how it looks. So, this is the sinusoidal motion that you are used to associating with the simple harmonic oscillator, right. And what we can do is we can either measure the time taken between, let us say, n number of oscillations and then divide by n, find out a time period, or we can simply take the time difference between two successive oscillations to find out the time period. Right. Okay. Now, we will start doing our experiment, but before that, where is the coupling? So, the coupling now will be introduced using this spring, right. It is a small spring which has certain spring constant, and this we will use to couple the two pendula and then study their combined motion. So, now what we will do is we will use this spring to actually couple these two pendula. Spring, I am coupling the two pendula. Okay. So, now this is a coupled pendulum, it is no more two isolated pendula. it's a coupled pendulum system, right, and the motion of one will be affected by motion of the other. Basically what I am going to do is, I am going to displace both of them by small angles, right, and approximately with the same angular displacement on each side. And then if I leave it, what you can see is they both keep oscillating, right. Again, if I can maintain, if the observer can maintain exactly same amplitude to begin with, then actually they both will simply oscillate as if they are oscillating independently, and the coupler will not have any effect on the motion. Now let us come to the interesting case, which is of beat, where we displace only one of them, and then we see energy transfer from one pendulum to the another and vice versa. Okay. So for this, what I will do is, I will displace only the one pendulum, let us say first pendulum, this I am calling as 1 and this is as 2. So I will only displace this one, and then you will see the motion as it evolves in time. So let me just displace it slightly. Right. So as you can see, I am not doing anything to the second pendulum, only the first pendulum is disturbed, and then I let it evolve. Okay. What I have done is I have given you time to observe this, and now let us go over the observation once more, where I will try to explain a few things, right. However, you might have already guessed or already seen what I am going to discuss. Let us displace it again. So now since I displace only one pendulum, right, what happens is this one starts oscillating, the spring gets stretched, because of that the other one starts to move. But over time, what we see is that the first one comes to a standstill and only the second one moves. Again, because there is stretch in the spring, the motion of second one starts disturbing the first one. So the first one again starts to move, and then again only the first one moves, the second one comes to a standstill, and this process of going back and forth, energy being transferred from one pendulum to another and then back to the first one continues. We will now go back to our data acquisition system, to the PC. We will measure this quantitatively, find out the characteristic frequencies, and then we will try to estimate using this system what is the spring constant K of this spring that is used as a coupler. Okay. So now before going for the measurement, let us see that what all things we need to measure. So we can make some kind of table like this, right, and that is what you will be doing in all the experiments. Handling the data and arranging the data in a proper manner is very important to do efficient measurement, right. So for example, here what I am interested in finding out is omega naught, then we need to find out, measure the beat frequency omega b, the oscillator frequency of the coupled system omega 3, right, and we will measure these two by looking at our data. To estimate the coupling constant K or the spring constant K, what we need to do is we need to measure these beat frequencies for different coupling lengths, right. So the distance at which the spring is placed with respect to the pivot point. So now let us start with our actual coupled pendulum experiment. What I have done is I have used L1 as 50 centimeters. I have coupled the spring between the two as shown earlier, and now I am going to give it the beat oscillations. That means I am going to displace only one pendulum by certain amount and let the system evolve. So let me start the data acquisition, and now I have displaced one pendulum, and as you can see on the screen, the oscillatory behavior or the amplitude versus time plot for one of the pendula is showing there. Fine. So now let us stop the measurement and now analyze it in more detail. So this is my raw measurement. As you can see, I have, so the amplitude change or the amplitude versus time plot shows me a high frequency oscillation as well as a low frequency oscillation of the maximum amplitude, right. So the envelope of this and the actual oscillation. Just to see it more clearly, let us smooth it out and change the scale so that it is visible. Right. So, this is your beat motion, and it is characterized by two characteristic frequencies. One is the frequency of the fast oscillation, which is omega 3. The second one is the frequency of this slow change of maximum amplitude, and that is our beat frequency. Okay. So, now let us go over these values which we have taken during this demonstration and try to do some quick calculations and try to estimate what is k. Right. Okay. So, the first thing I will start with omega naught, right, and we found out that the time difference between two successive oscillations as 3.677 seconds and 2.159 seconds. Right. So, the difference between these two gives us delta, and this delta corresponds to an omega naught of the about 1.8 radians per second, 4.18 radians per second. Now, we can go for omega b, right, and so we have to do omega b for several values. However, I have shown you for one. So, let me write down the values for that, and the difference between two minima, successive minima, was 34.349 second and 13.365 second. Right. So, you can find out the corresponding time difference. It is about 20 seconds, right, and with this we can find out the omega b, which in this case then comes out to be 0.15 radians per second. Right. Okay. So, this is my omega b, and let us rectify some mistake which we did during the demonstration. I told you that we are doing this demonstration for the coupling length of 50 centimeters. However, what we did was this was taken for 40 centimeters. So, that means for L equal to 40 centimeters, omega b is 0.15. We can also estimate what is omega 3, the oscillator frequency. So, again we have to use the same time and simply divide by the number of oscillations within the successive minima, and this was 14. So, you can find out what is the time period for individual oscillations, and from there we can find out what is omega 3, and omega 3 comes out to be 4.2 radians per second. And now, so these are the quantities that we can find out from here. We went ahead and made these measurements for remaining 3 lengths, and I will simply write down the omega b that we measured here. Once we have this, now I can plot to estimate the k, I can plot the ratio this as a function of length, and what we expect is that if we can divide the y scale, whatever is the number, omega naught is known. So, you can always find out what is the quantity under the square root. Right. What we want to see is that it shows a linear behavior. So, because this quantity is directly proportional to the coupling length L, these points should fall on a straight line, and by fitting a straight line into it, we can find out the slope, right, and from this slope, which is then equal to this quantity k over m g L. Right. So, slope is equal to this, and from this slope we can actually find out what is the value of k.